Hi everybody. In this video, I'm just going to explain the magnetic force on the current carrying wire. In the last video, we found the magnetic force. We talked about the magnetic force in the over the charge, when the charge is moving in the magnetic field. Now we're going to talk about the straight wire when the current is going through it, and there will be a magnetic force over that current if the wire were in the magnetic field. So we have two conditions. First, you should have a magnetic field. Secondly, you should have a wire when the current is going through that one. We call this one the Beal formula, magnetic force on the current carrying wire, current carrying conductor. If you have a straight wire, as you see over there, that's a straight wire, and the current is going through that wire, and we put that wire in a magnetic field, which is an external magnetic field. It's not a magnetic field by that current. It is not the magnetic field by that current. It is the external magnetic field, by the way. So you see, we're going to use our right hand rule for indicating the direction. The thumb shows us the direction of the current, which is going to the north. And the field, it's cross, so it means B, it's into the port. My forefinger is into the screen. And as you see, my palm is going to show us the left side, which is there is a magnetic force over that wire to the left side. This is how we're going to indicate the direction of the magnetic force over the current carrying conductor. And the magnitude, if I want to find the magnitude of the force, I have to just say magnetic field times the current times the length of the wire. So Beal formula, we call Beal formula. B, magnetic field, Tesla, you know that I is the current and L is stand for the length of that wire. Okay, now this part is quite easy. This part is quite easy, but if you have two parallel conductor or two parallel wire, in that case, we will have some conditions. Because, you know, each wire that you have and the current is going through that wire is going to produce a magnetic field around itself. Another wire beside of it, so it will be affected by that magnetic field. So there will be a force of the beside of the first wire. So what do I mean? That if you have two straight wires, as you see in that figures, if you have two wires, when the currents were in the same direction, as you see, first one, A, we have two wires, the current is going through that wire. The I2 and I1, they will have a fields. So B1, if I use my right hand rule, I see it is going into, that's going to be B1, and it's coming out from that direction. That's the direction of the B1. Okay. And for the I2, I see that is going into, as you see, it is going into from that side of the wire, and it's coming out from that part of the wire, which is, that's a B2. Now, if I want to have an external magnetic field over the wire 1, I should take that magnetic field. I cannot use the magnetic field of its own current. So that's why I'm just going to remove all the magnetic fields from the first wire. I will just have a B2, which is all out of the board. That's why we write out of the board, as you see. So this is all B2 from that side is out of the board. B2. Now, if I want to write down the formula, force magnetic over the first wire is equal to what? Is equal to the magnetic field of the second one times the current of the first one and length of the first one. Look, I said external magnetic field, so it means the field from the other wire. It cannot be the field of its own wire. Okay, so same thing will be applied for the second one. And for the second one, I see the magnetic direction of that magnetic field, it's cross, it's into. So it means from the all of the area from the right side of the first wire, it is into. So the field is into, that's why we draw into. So that's going to be B1. Sorry. Now I can write down the F2 on the wire 2, magnetic force on the wire 2, by writing that formula B, I, L. Because it's 2, the current is second one, of course, the length of the second wire, but the magnetic field must be external, which is the first one. This is the way we're gonna write down the direction of the magnitude of the force on the two current carrying conductors. So if I use my right hand rule, I see that these two wires, if the direction of the currents were same in these two wires, the wires will attract each other. The wires, they will attract each other up. And if I have two wires this time, but two different directions, one of them up, other one is down, so the currents were in opposite direction, in that case, the wires are going to repel each other, right? How do I know they're going to repel each other? What is going to be the direction of the magnetic field 2 over that area? Okay, so let's look at the I2. I2 is coming down, so it means the thumb is down. This forefinger, the forefinger is going to show us this 4, it's crossed is into. So when it is crossed, it means all of the side of the wire, it's crossed. That's why we're going to write B2, it's crossed. So now field is into, and the current is going up. What does the direction of my palm is going to show me? The left side. That's going to be the force of the F1. If I want to find the direction of the F2, I have to just remove that part and I have to follow the direction of the first magnetic field. First magnetic field, it's all into the page from that side, isn't it? That's why we just crossed all into the page. So it means B1 is into the page. Now, B1 is into the page and then my thumb is 2 down. So I will just use my forefinger, it's into, okay, my palm, then my palm is going to tell me the right side. You see two different forces, two forces which are the opposite direction, they will just repel each other from the wires. I hope you understand this explanation. And there is easy questions about this one from the Wizari. Look at this question from the Wizari last year, 2020 to 21. They asked this question. They say you have a wire, it is in between two fields, and you know that the magnetic fields are going from the north to south. This part is important, so that's going to be the direction of the magnetic field. How you can indicate the direction of the force? So your forefinger shows you this direction. This is 4 fingers, and direction of the current is to the up. So that's going to be my thumb over there, right? That's going to be my thumb, and that's going to be my 4 fingers. And then I can see my palm is toward you and out of the screen. Let's just clean this one up. And that's the direction of the field. That's the direction of the current, means the thumb. So direction of the force, it's going to be out of the board or out of the screen. Direction of the force, sorry, not field. Okay. So when the direction of the field change, also direction of the force will change. We have this Wizari question. It said that one current is going down and the one is going up in that figure. The question said, what is the direction of the magnetic field B1 at the location wire 2? Find the B1 at that area. Okay, so if I want to find the B1 at that area, I have to see this is going to be the direction of my thumb. And if it is direction of my thumb, it means my forefinger is going to go into the board and coming out from that side. This is all into, and from that side should be all out, isn't it? So when I say out, it means all of the side is going to be out. All of them is going to be the out. Okay. Out. That's going to be B1 from the location of the wire 2. So it means out of the page. Okay. Let's go for solving some questions. We have this easy question. Let's just read it. 36 meter long, carries a current. So this is the I, this is the L, and from the east to west, that's the direction. From if the magnitude of the force of the wire due to the earth magnetic field downward toward the earth and has a magnitude of that force. So that we have the already force, find the magnitude and direction of the magnetic field. So we need to find the magnetic field B and direction. First of all, for finding magnitude is quite easy. Force is equal to BIL. So if I want to find B, I have to just say force over IL, as you see. So we have the amount of the force 4 times 10 to the power -2, and we have the L 36 ampere 22. We're going to get that value. Why it is due to the north? Let's just look at the question. We have the question is said that from east to west we have, so it is going to be okay, so it is from the east to west. So the direction will be into that direction. That's going to be the direction of the current, as you see, east to west. If the magnetic of the magnetic field downward, it means toward the earth. So it means it's into, that's the force. What is going to be the direction of the magnetic field? So my thumb, it should shows me that direction. And my palm, it just shows me the into. It means it should be toward the screen. And the forefinger you're going to see is going to the up, which is north. Okay, I explained the right-hand rule in the video. You can just check. We have another question. Again, it's going to be the same thing. And it's asking for the direction. A 6-meter wire carries a current 7 toward the positive X. So it means it's positive X. That's the direction of the current. And the magnitude of the force is toward the negative Y. That's going to be the direction of the force. What is going to be the direction of the magnetic field? So my palm should shows me that way, and my forefinger, my thumb should shows me that direction. And as I will see, this forefinger is going to be out of the screen, which is that's going to be the symbol. Sorry, out of the screen, positive Z. And that's it. And the magnitude is quite easy. You can just find it out by yourself. We have that question. We just did it at the up. It is Guzari question, by the way. Okay, we have this question from chapter review, question 22. Let's just answer that question. On 1 meter long copper rod, uniform magnetic field has a mass of that 50 grams. Okay, when the rod carries a current, that one, I have I have the mass, and I have L. It floats in the magnetic field. In the magnetic field, that's so much important. What is the field strength that the magnetic strength of the magnetic field? I have to find the B. Guys, when the question is said it floats in the magnetic field, so it means it has a magnetic force which is equal to the gravity, equal to the gravitational force. That's why we write F magnet is equal to Fg. So you know that F magnet is equal to BIL, F magnet is if G is equal to Mg. We have the Mg, mass and the gravity 50. It's a gram, we have to change it to kilogram multiplied by -3 or divided by 1,000. 9.81, that's the gravity, you know already that one. L is the length, and 0.245 is going to be the current. We see we will get 2 Tesla. That's going to be the D answer.